To 4 o'clock, so I think it's time for us to start. So welcome everybody to the Fields Institute and to the distinguished lecture series of the thematic program on set theoretic methods in algebra, dynamics, and geometry. My name is Deirdre Haskell, and I'm the Deputy Director of the Fields Institute. And so it's my pleasure to welcome you all here, and actually to welcome the thematic program, because I didn't do an official welcome yet, so very happy that you're here. I know we're well into it, sorry. So for those of you who are not here in person, the Fields Institute for Research in the Mathematical Sciences is located in Toronto, Canada. The mission of the Fields Institute is to promote fundamental and applied research in the mathematical sciences, understood in the broadest sense. We do this by bringing people together to facilitate the communication and collaboration that sparks new ideas. The Fields Institute itself is located on the traditional lands of the Huron-Wendat, the Seneca, and most recently, the Mississauga of the Credit River. This meeting place is still home to many people from across Turtle Island, and we acknowledge and express gratitude for the opportunity to live and work on this land. The Fields Institute is funded primarily by the Ministry of Colleges and Universities of the Province of Ontario and by the Natural Sciences and Engineering Research Council of Canada, as well as by a network of 9 principal sponsoring universities and other sources. It's a great honor to host today's speaker, Stevo Todorčević, who will give 3 talks for the distinguished lecture series. I will hand over to Justin Moore, who will tell you more about our speaker.
Okay, I think for most of you, Stevo doesn't need an introduction, but I figured I would give you an introduction anyway, because I think he deserves it. So Stevo got his PhD in 1979 from the University of Belgrade. He had several postdoctoral positions in, I believe, in Jerusalem, Dartmouth, Berkeley, and spent some time in Boulder, Colorado, before largely, becoming a permanent fixture in Toronto and then also in Paris. He's been an ICM speaker, an invited speaker at the ICM. He's held a Canada Research Chair and is a winner of the CRM Fields PEMS Prize. He, I think, perhaps more than anyone, has really kind of put forth the role of Ramsey theory as a kind of a paradigm for classification and foundations within mathematics. He's done a lot, made many different diverse contributions to the combinatorics of uncountable sets. This includes the method of minimal walks, the development of models, building proper forcings using models of side conditions, studying the combinatorics of SNL spaces, the theory of Borel combinatorics through the G0 dichotomy and chromatic number of Borel graphs, and also the Kekres-Pestov-Todorčević correspondence, which kind of develops a dictionary between structural Ramsey theory and the dynamics of Frisé structure, automorphism groups of Frisé structures. So I think without further delay, let me hand over the floor to Stevo.
Thank you. Does this work? Yeah, okay. Okay, so there will be, as said, this will be a series of three lectures. The first one is the most basic, as most somewhat general, and so in other words, requires very little knowledge of mathematics. Just and on the other hand, it does point out to one phenomena which we are going to explore later in other lectures. And so let's see. Okay, first of all, what's the basic problem? It's you have a class of mathematical structure with and the connecting maps or embeddings or homomorphism or homeomorphisms or homomorphic embedding, all various. So this pre-order or pre-order relation is the connecting maps. You want to have you like to find a basis, a critical structures somehow present in every other structure. That's some basic problems of that sort, very general. We'll see specifics. That's typically you want to have a finite basis, but we are going to give a interesting example that maybe there are also very interesting theory to be developed when the basis is not finite, but that you can actually enumerate. And so this is another variation of the problem, which is actually even more older, which actually perhaps the first very well-known comes in this Kuratowski characterization of planar graph. You take a class of structure, you like to characterize its subclasses that are normally closed by forbidding finitely many members of K. And if you know a little bit about the classification programs of, say, ultra-homogeneous structure, you'll see, for example, in the case of the graphs, the amalgamation classes of graphs are usually given by forbidding various configurations. But if you like to look at it in a very abstract way, in a much wider form, you would like to really find for example, in the case of the linear ordering, something like this. Can you characterize finite linear ordering this class of all, linear ordering, counter linear ordering the class of all, and the third one is still open. You are going to actually present the solutions of these two. They're still open that you can characterize. So solution to a basis problem is another metrization problem. It's a solution to a metrization problem. You'll see in the context of topological dynamics, we do have a metrization problem. We do have a solution of metrization problem of some invariance using the method. And this method, this is where everything started in a paper of Ramsey with this title. It's a decision problem. That problem was popularized by Hilbert and Ackermann in the 1920s. His paper was the end of the 1920s. There was previously some attempts to find a procedure for deciding the validity or consistency, equivalent consistency of certain statements. Of course, today we know that there is no that the problem has a negative answer. It is for generality. I think it was done by, say, in the 30s by Church and Turing, but he was concentrating to a particular kind of sentences that have in a Prenix form just a universal converse on front of it, and then an arbitrary combination, Boolean combination of the atomic formulas. So that's you like to solve this problem of consistency or to solve this decision problem, and this is a notion which was really implicit in his paper. It was really pointed out by Ascolem in a paper which nobody is not actually in his even MathSciNet base. The paper of Ascolem 1933, which goes very carefully over Ramsey's paper, reproves the Ramsey theorem and gives a little bit better upper bound, but what he isolated is this notion, which is actually crucial. In other words, you want to solve a decision problem, so the solution of the decision problem is saying, well, you find a one expansion, in this case, this ordering that somehow captures everything. The ordering on the natural numbers captures arbitrary relation. So this way we are going to go. I'm going to. I think this does this. And there is no. Okay. There's no light here. Okay. Okay, so this is actually a theorem that they proved. Actually, Ramsey did not state it this way. Say if we have a set of universal sentences, then if you have integers m, you can find integer n that depends on the number of relations and variables just number of relations and variables. and on this integer n, so that if there's a model of a size n, then there's a one canonical one of this smaller size. And so what I really have is this, they have solved particular instance of this problem. So you have your given structure, and you want to expand it to capture arbitrary relations. And now you're capturing, meaning that the arbitrary relation is simply definable, meaning that no existential quantity, just using atomic formulas. And on the large substructure, large here is interpreted from the point of view of the original structure. So this means large will be something like the best you can hope for, say, is isomorphic to the original structure. Some substructure is isomorphic to the very rationally captured, but typically you are satisfied with much less. So simply definable, we are going to actually even be even more specific with this simply definable. And we are also going to be interested how many of relations you need to add to catch everything. And so there are various versions of this problem. And let us see what the Ramsey and Column what they have done. So interesting, I put n equality. Usually people don't mention equality when they write, when they state a theory or something, but which means you start the set with no structure. And sometimes you don't have equality, sometimes you can define it, but think about it that either you have equality or you don't have any relations. And in some sense, this is how Ramsey started no relations, although his formulas do involve equality. Okay, so that's for this structure. You can think about it as a no structure. Why this is a no structure? Because being isomorphic to original structure is easy, right? Just being a large, say simply cardinality, or infinite. So being what I want to say. So now I'm doing something. Yeah, but I want to go backward. This is going backwards. Okay, so this notion of a large being isomorphic on a large set is easy. No structure tells you that this is not such a big requirement. Nevertheless, the canonicity is non-trivial, meaning the being simply definable. So what is the solution? Solution is simply adding the ordering. It's not in fact any ordering. The best, of course, is just to use the usual ordering of n. And here is the definition. Well, as I said, the relation is going to just look at the a given k tuple. Relation is going to be valid depending of how these terms are related in the ordering. So this is the translation that they have the same pattern. These are atomic canonical relations. Obviously, you can enumerate these. Of course, the enumeration probably may not be particularly pleasant, but is possible. These are called atomic canonical relation. Any other relation is simply a union of these. Canonical is simply invariant or just a union of these atomic. So, for example, it's very easy to do this for dimension 2, but dimension 3 is also possible, but it's not so simple. A longer list. The point is that if you want to have a formula that involves just binary relations, all you need is just check on these. That's the point. So that's why you have a solution of the problem. And now what is the key behind it is Ramsey's statement. And this is what Ramsey did. And you see, it's interesting how would you can state, how would you, the people state this, there are lots of different forms. What is that you are, so for every point, so you can, you can well, I should have said every atomic relation. Although this is also true, but okay, what you're really interested in every atomic relation is, sorry. So again, I have to go back. So what you are coloring there is expressed in the terms of the expansion. You can, if you do not have an expansion, you would say set all tuples that if equality was there, you would say xi differ from xj. Okay? And then you will have a problem with proving this version of a theorem. And then we have this corollary which Colin pointed out, that every relation is captured is either contained or includes this atomic one or is disjoint from it everywhere. It's the immediate consequence of the. So which is meaning that every relation is canonical. So all relations are captured by one single ordering expansion. That's a very strong solution to the expansion problem. That the relations can be, the important relations can be numbered. And that word canonical was really not the one that they used. That was really Eldorado. I'm not so sure what their relationship. Of course, they knew Ramsey's, but I don't know. It does look like they knew Colin. So what they did, they know that arbitrary relation is canonical. There is a tedious problem to actually classify them, right? You put your relations of certain kind and you say, what are the canonical ones? This could be a tedious enumeration problem. What they concentrate themselves on the canonical equivalence relations. We know by Ramsey theorem that all of them are canonical modular restriction, so there's no need to look any other. What are the, again, the equivalence relation on this index set are really a relation on the n to 2k. On the twice. This is actually how they are proving the theorem. Anyway, so the canonicals are really given by a subset of the index set. Two things are equivalent if they have the same restriction on the index set. And there are 2 to the k many exactly, so it's a very pleasant classification result. It's not particularly difficult to remember, etc. But if you, as I said, if you go to arbitrary, if you want to classify arbitrary relations, remember in the measure tool we had the 8, but if you go to the higher one, you get quite a much more complicated classification problem. Anyway, they thought this is in form of the coloring. And they thought this is really extension of the Ramsey theorem, because if you take equivalence relations with the finitely many classes, this I is empty. So you get a constant. Only one class present. So they thought as a result, as an extension of Ramsey theorem, of course, they use Ramsey theorem for it. Okay, so now if you combine Ramsey, Colin and Ramsey, you have this usual way you stated. Every equivalence relation has a restriction equal to one of these. So solution to the basis problem. There's a 2 to the k minimal ones. Okay. There's one interesting corollary that has been pointed a little bit too late. There's a very large interest, a very huge interest in what one can prove in combinatorics from the time arithmetic. And this is the one I would like to mention it because it's a curious situation. This is one of the consequences of the Eldorado theorem, because if a mapping is regressive, this index set I can be either empty or could include minimal point, namely the 1, or actually 0. The subset of 0, 1, 2k minus 1, 0. If it's 0, this is exactly mean homogeneous. So immediate consequence of infinite Ramsey theorem is this theorem. Now, if you want to finitize Again, I'm doing the same. I want to go back. If you want to finitize this, there's no actually problem because this is a consequence of the 2k-dimensional Ramsey theorem, which has a finite proof, meaning a proof in Peano arithmetic. So this theorem has a finite form of this theorem has a proof in Peano arithmetic. But this theorem, this consequence does not have a proof in Peano arithmetic. That's one of the curiosities. This finite form of this is not provable in Peano arithmetic. This was a result of Kanamori-McAloon, coming, of course, after Paris-Harrington and others. Okay, let us look at a little more complicated structures, rationals. Now, again, the rational with the usual ordering. And now notion of a largeness, you want to canonize it on the large substructure. Now the large cannot be any more infinite, because that's, if you I say infinite, then you are in the previous problem, which has been solved. So now large would needs to be isomorphic, order isomorphic to Q. And the expanded structure is, again, well-ordering. The expansion you guess is a well-ordering. In other words, enumeration of rationals. You want to hope, so this is typical in the classification problem. You first make a guess and you will try to examine whether this guess is correct. And it turned out to be correct, but after lots of work. Okay, so this is the expansion with this well-ordering. So they interact in the natural way. There's a natural equivalence relation. You simply see how the ordering is intervening. You can also think about these in terms of the trees. If you have a linear ordering and a well-ordering of type omega, there's a natural tree there always. So you can think about these terms as well. But let us not. So somehow there's a natural tree there. And canonical means simply union of these basic ones. And the key result again, atomic canonical relations are Ramsey, meaning that you cannot split, meaning that this tells you this is it. This captures, this expansion is the right one. Of course, doesn't mean that you solve the problem, because there's also an enumeration problem. It's telling you what are the canonical ones, which one are important and which ones are not. So it could be quite, and in this in particular case, actually, it was quite tedious. So arbitrary relation is canonical, meaning it's described by this interaction between the well-ordering and the usual ordering. There's nothing else going on. So union of the atomic, every relation is in the atomic ones. Being described. You see how, when now we say it's a simply definable, simply union is a Boolean combination of the. You are using some canonical one and you are disjoint from some other, and nothing else. And now this is the, so class, and now it's you see the notion of essential changes depending how big set you want. Essentially, which is present everywhere, meaning in any set which is order isomorphic to Q. Essential being that is unavoidable, as long as you're keeping the notion of largeness. So this is the problem to classify. This is actually what Rich Laver did not want to do. So this is enough. The other one, and that was done by Devlin, which had a very nice classification result. So he just looked again in the same canonical ones on this increasing relative to the rational ordering. These are increasing relative to the rational ordering. Of course, if you know these, you know any other. Okay, so it's a very one, and then if you use them to form a equivalence relation, then you have this corollary of a positive and the classification result. We say in every equivalence relation on this particular power, there is a copy of rationals where this equivalence relation is coarser than the given one. So again, the solution to the basic problem. The coarser than the given one in a very in a very concrete way. Not only, you don't need the embeddings. Typically you would say you need embedding to move. Actually, you don't, you just need the restrictions. Somewhat stronger solution. And now you will say, where is the problem of formal logic? It should be somewhere, right? It was there, so it should be also here. And it is in set theory. In analysis of axiomatic set theory. You take this system and you have this special axiom of choice. You like to see its relationship. It's a typical thing that one does in set theory or mathematics of set theory. You study models. So you're interested in constructing models of some of these, but not some of the other ones. Particular case is the AC. And this is the standard consequence. There's a book of them, but I just randomly picked one. Two are standard formulation of and I'm interested in the last one, the Boolean prime ideal theorem. Every Boolean algebra has a maximal ideal, or every Boolean algebra has an autofilter, if you like, the dual form. Something that strong representation theorem relies on. Okay, so it's a well-known contribution. It's a great contribution by Gödel by he constructed the universe. Every model of ZF has this inner model of constructible sets. And after him, it was not clear where AC is actually a theorem. And there was a problem that the problem in formal logic that is behind the Lever and Devlin is exactly this. So the problem of formal logic that is responsible for the Lever-Devlin's classification result is exactly this problem. Does Boolean prime ideal theorem implies AC? Let's see how it is done and what's the connection. Okay, you start with a transitive. You might be worried whether we have it, but let us not worry about transitive model. Set a model of ZF. We can assume that it's an actual model of ZSC by going to a constructible universe over it. And then you, what we call add a count many quadrials. So omega is there, so this counter space is there. But of course, not all members of the counter space is there because M is countable. But of course, M can code open sets and basic open sets. And it can code open set as a union of collections by a collection of basic open sets. A code of open set is a collection of basic open sets, or a code for basic open sets. So since there are count many dense set, there is a real which is there, and then you pick it. And using this Cohen method, there's a minimal, very natural extension. That's the model is a symmetric model. It's tedious here to actually, there's some mathematics about the invariance. So the members of MC are given by names. You look at the invariant names of the various group of permutations that just act on the first coordinate, which means the groups of permutation that moves the omega quadrials. But there's so you form this intermediate model. It's very natural. As a matter of fact, there's another description of it, which is more, maybe even it's simply, if alpha is the ordinal height of omega, then this is simply L alpha of a C, not square bracket, but being that you start with the Gödel process from C union C, everything you can define using parameters from C using the set C itself. And this is the basic contribution of Cohen that ZF is true there and AC is false. Sometimes they said C cannot be the order, and in SAT actually much worse than that. And this is the solution to the problem in formal logic. Says Boolean prime ideal theorem is not consequence of, doesn't imply AC. So it's weaker. So it's a proof that it's weaker. And it turned out that there's a combinatorial theorem behind that is again equivalent to the statement of the theorem of Levy and Halpern. Combinatorial theorem, which I would like to describe, which I think everybody should know, that's equivalent to the statement. This is the Todorčević theorem. Okay, so let us see. It's about an interesting set of ideas. So the objects they deal with is the rooted finitely branching tree of height omega with no terminal nodes. So finitely branching tree root. You'll see it actually is this is the finite theorem, really actually not an infinitary theorem, but it's good just to state it is. Okay, so nth level is the distance from the root. This all nodes that have this distance. And there's that cone, I mean, the central thing that are comparable with x. So this is some sort of a cone subtree. And there's that notion of a k-dense. A subset is k-dense if it dominates every node of height k. It's a metric notion. If you want to think about it in the mathematical terms, this is a notion of a epsilon net in a matrix, in a totally bounded metric space. It's analog to the epsilon net, where epsilon is 1 over k or something. So dominate every. I'm going to give you a picture. This is simply a kx dense if it is dense on a subtree of that sort. And somewhere dense, and now there's important here. There's a k. There is x. X is somewhere dense if you can find a k and x where you are kx dense, but k has to dominate x. Otherwise, if a k is below height of the x, then being k dense is a trivial notion, simply one singleton. It's not said being a kx dense is one element can be. So it's anyway. So this is the way you should think about it. So k dense is dominating this. Kx dense is that. That's very natural. And now we want to take this into the product. And the product is take coordinate-wise ordering. It is not a tree, but it's better to think about it as not a tree. Sometimes one likes to state the theorem in terms of the product trees, but anyway, this is just a partial ordering. A grid, originally Todorčević wrote it as a matrix. Anyway, it's a subset, it's a subproduct. A grid is simply a subproduct. And k-dense, meaning that each of the factors is a k-dense in a corresponding tree. And kx dense, x is also a node, doesn't need to be at the same height. All the kx dense, if it is each xi is a k xi dense. Somewhere dense, again, if it is a kx dense for some k above the height of each xi. Again, you don't want triviality. If it is below height of some xi, this coordinate disappears. So your problem is not to dimension d, but of some smaller dimension, and you want to keep the dimension. And this is the picture. Product of these dots, there is the grid, and the product of these dots is kx density, and is a somewhere dense if it is above, as it is on the picture above. And this is the remarkable theorem. You see an arbitrary sequence of finite rooted trees of height omega with no terminal node. Every p, there is an integer n. So this is the n. You see so we don't need full tree. There's just n. It's a finite theorem. Of course, the tree themselves might be a strange tree, profusely branching or whatever, but there's always this n. So that for every coloring is constant on a somewhere dense subgrid. It's a kind of a metric notion of a. This theorem has a lot of similarities, a kind of a product theorem, and has a lot of similarity with the Hell-Jewett theorem. And the variation of a Hell-Jewett theorem that gives this theorem where the trees are uniformly branching of a bounded But if the tree is not, this is really far, and in other words, the power of this theorem is exactly there. Basically, the standard proofs, if you want to prove this theorem by some kind of inductions, that the standard proofs that that usually go into that you're building your object from below up. If you're doing induction, you're having something that is good for a smaller. Depending where this is, the notion of a largeness can become much unpredictably large because of the height. The largest height gives you a bigger. This notion of a denseness, kx dense, requires you to say this last coordinate to be much bigger than you could have predicted. There is no prediction in advance that you know how large the sets. So there is no prediction in advance to know how large these sets YRs are going to be. I think you don't know. And there's a very pleasant way to state this result. So that, and most of the people, for them, this is it's a restatement of this result, if you wish. Again, take this true, and then there's also a strong subtree. So some tree that copies the original structure. In other words, it has to. Its immediate successors of the subtree have to be k plus 1 x, then it's a subset where k is the height of the node. So there's a level subtree, and if you take a node of a given level, you want to see what is doing, what is the next. You have to extend every immediate successor of S in T, and there's no show of strong subtrees of a given height, including infinity makes sense. And this is the picture of a strong tree. It's unfortunately there's some little lines up. They should all be there. This is height 3, so there's this dot, bigger, thicker dots. This is the subtree. There should be also thicker dots up, and this ends there. You can of course continue. The height 3, yes. So you will never. So this somehow corresponds to the k-element set. If the tree is just omega, just a branch, this is really simply a k-element set. So every k-element, all k-element sets are isomorphic, right? But not all strong subtree of height 3. They don't even have the same canality. Strong subtree of height 3 can have a strange canality. Maybe the canality can go to infinity. So you see, it's a different. If you fix a k in the case 3, you look at around this. There is no. You can color according to the canality or some invariant of the canality. And actually, it turns out that you cannot. No matter what tree you take, and if you're usually branching, you color the strong subtree of that height. There is a strong subtree of infinite height with this constant. Use of this theorem for the purpose of the Lever and Devlin is for the k is binary. A t is binary tree. So in this case, and in this, as most of this is the most of the time this theorem is used. It's a rather straightforward consequence of hypergraph theorem, but is a beautiful theorem. So I just want to point out the strong tree of this is exactly this. So Ramsey theorem is a consequence, right? Okay. And now we go to the random graph. We could have used the same theorem to solve the expansion problem for the random graph. And this has actually been done with basically a very similar set of ideas, except, of course, the classification problem is much more tedious. than in the case of the rationals, and they have been done. Although here we don't want to do this, but we want to do a variant of this problem. Okay, so what is the random graph? Is okay, the structure which we put on N to be easy to talk, to be easy, so that we can talk it. When we do expansion, it will be easier to pick it. Okay, so that's the very well-known object. And that's the variant of expansion probability on the arbitrarily large finite subgraph. Arbitrarily large in the following sense, you give me a finite graph, then I want to canonize a given relation on a induced subgraph of R that contains a copy of that graph. So arbitrarily large, not in the sense of cardinality, but in the sense of embedding particular graph. So it's not a sense of cardinality. Okay, so here, for this purpose here, since there are no ordering, you see there is no ordering here. And you see the R is the irreflexive relation, you know. So there is also, there's that, what I want to point out, there is that equality relation. Of course, you can add, if you like, it doesn't hurt, but it's interesting. Anyway, this is the, in other words, if you want to solve an expansion problem, it's sufficient to look at the subrelations of that. That's the point. Because you see, if you, any other relation might, is going to permute these in any other form, or even ignore some of them, and then you go to a smaller dimension. So in other words, if you essentially of this dimension, that's where you need to look. And this is a Nash-Rodel expansion for the random graph. And that's why I put this Nash-Rodel, because you see, Ramsey, finite Ramsey theorem has its own life in combinatorics. And there's a very natural line of research that eventually ended up in something called structural Ramsey theory, where the people are solving some kind of a Ramsey type of problem until they arrived at a situation of graphs, something around in the 70s. They were in some sense forced to do this, although they did not state it in this form. In other words, they were forced to go back to the original Ramsey formulation. In other words, the problem, Ramsey theorem went to a problem in first point graph theory by Erdős-Eckers, and then moved in various directions, and then come back to original Ramsey-Skolem formulation, which is this. Okay, so, and now expansion is not a well ordering. Expansion is a homogeneous ordering, and in some sense homogeneous if you put them together. So is universal relative to all finite ordered graphs, and it's homogeneous as a homogeneous structure. That's the Nash-Rodel expansion. It works for lots of other homogeneous structures. I just picked this one for some reason, just to make things easier. Because all the ideas, most of the ideas will be there. Later on in some lectures, we'll actually go to the general theory, but this is the one. Okay, so now you take a finite graph, and its vertex set 0, 1 to the k minus 1, yeah? And now we know we have fixed this expansion, so we can look at the canonical relations. So this graph A, gets its canonical relation. So what are the set of all one-to-one tuples that preserve the edge relation? You know, copy the original graph, the copy of the original. So what is this? So simply, if you want to think about in the structure, so this is the collection of all embeddings of A into R. Right. This is the collection of all. So canonical relation here is you see canonical relative to which structure? This is canonical relative to the random graph structure, not canonical to the other. So this is so every final graph gives you a canonical k-array relation. So you have on a particular k, you have as many of them as you have a graphs on the vertex set, 0, 1 to k minus 1. Okay, so that's the way you should. I'm not going to use this other notation, embedding array, just a CA. And the Nash's order expansion splits this in its own. What are its own? Well, set of members that what are doing? They are embedding. That, of course, you have to be a little. So suppose if a sigma is identity permutation. So this is the set of all embedding of the original graph VA enumerated, in other words, ordered as a 0, 1, k minus 1. Then this becomes x0 less than xi less than xj. Now, if you are permuting, you are changing your split. So this is the splitting. This is splitting C of A into k factorial disjoint pieces. That you have k factorial disjoint canonical translations. Canonical of the expanded structure. And this is the result. So there is an arbitrary defined do subgraph, so that this is canonical. I mean the union of a canonical ones, atomic canonical ones. So this is the particular way on states in the terms of embedding. If you have a fixed graph on the vertex set, and you fix a permutation, then these atomic relations are Ramsey, which means that for every other relation, it's either disjoint or it's in. In other words, no relation can be independent from. You cannot split atomic relation into two important pieces. That's usually how it is stated. The point here for Nash Rodler that they went further, and actually today they have a general theory. It's actually been exposed here in the first workshop, but I want to point out that this is actually there's a very general method behind proving the theorem of that sort. And again, there's an arbitrarily large finite, meaning you are writing in this form. And there's that key notion and the ordering property. And why suddenly have, or let me write it and see why do you need that? Why they would ever consider this? See, class finite has an ordering property. If a finite graph, there's another finite graph. The arbitrary graph in order graph, there's a finite order graph. So that no matter which ordering you put on the first one, there's embedding. Why somebody would want to prove that? It looks like a curious thing, but this is exactly showing that these classes, they are all essential. They wanted to solve the classification problem, that all classes CA sigma are essential. The order of them can be, so this is the reason why they were saying all classes are essential, meaning that they are present everywhere. You cannot shrink this further. So ordering properties are very natural fact. If you want to solve the basic problem, it's a classification problem. You need to see what are the important invariants. You have a finite graph. You have a finite subgraph of the random graph. What are its invariants? Which kind of invariant you can attach it? And he simply said the only invariant is a permutation of the vertex set, nothing else. That's another way to think about it. And they're all important. Ordering property tell you that they're all important. And this is one of the corollary that somehow, if you read this corollary, you somehow recognize some other phenomena, other fields. So again, you take a finite graph. So this is simply a combination of the two. You take the finite graph ordered. So if you look at these canonical n factorial many classes, on this set of all embeddings from A into R, which is that set CA. So C index A is a split into these. They're all essentially the ordering property, and this is the Ramsey property. Yeah. So there are two properties. That they are all important, that they are all visited, and the second one, that any other must be coarser than this one. In other words, it must be simpler. Any other equivalence ratio with finite many classes must be simpler than this one. It captures, in other words, it's a basis result. So if you like to look at the equivalence relations with finitely many classes, there are 2 to the k factorial, many of them, right, or -1 if you disallow empty, right? Okay. And this is the
so
yes.
you say arbitrarily large here.
Every final graph, for every final graph, there is another final graph. There is another final graph on which this is canonical, and your graph embeds. And not in terms of canonical, but in terms of terms of what people call age. Right. And here is the reformulation of this same result in terms of dynamics. It's the same result, again, from the solution for the solution to the expansion problem. We learned that your key action must be on the linear orderings. That's what you learn by looking over the shoulder of these people. You see, well, they are doing this. Look at the natural action. It's called logic action. You push linear ordering. This is a compact space. There's a natural action. It's actually minimal. This is the first result there, actually. This corresponds to this ordering property. This is the ordering property, and this is this universality. In other words, the 2 points correspond exactly to the 2 points previous. And in the later lecture, we are going to actually see what is the most general form of this. And actually, we'll see a very general form of this is true. And here is the second paper. It's really a great paper. It should have been better known. Thank you.